Hey, welcome back. So now we're trying to actually connect all the theory and methods that we've accumulated here to kind of the main purpose of this whole chapter, which is to find out what things like sine of 0.5 are equal to. Okay, and it'll turn out we can accomplish this by kind of viewing this as an infinitely long polynomial. So sine of x we'll think of as a series. Okay, the series in particular of -1 to the n plus 1, I believe, and then x to the 2n plus 1 all over 2n plus 1 factorial. Okay, it'll turn out that those things are the same, and we could use that to do an approximation of sine for any value we want. Okay, so that's kind of what we're going towards here in chapter 9, and we want to begin now that connection between the series and these functions like sine of x, e to the x, ln x, the functions that you probably wouldn't be able to evaluate unless you had a calculator, right? Because you can figure out stuff like sine of pi over 2, we know that's 1. But if you needed to figure out what's the sine of 1.5, which is close to pi over 2 but not exactly, how the heck would I figure that out? How does the calculator figure that out? It turns out we're going to be using these series in order to pull it off. The calculator doesn't use series. It turns out that I think like during World War II or the Korean War, somewhere in there, the bombing guidance systems, kind of the way they developed those, produced a method for computations that the calculators use. But I mean, just in the beginning, how the heck were they able to figure out these values, right? Isn't that an interesting question? So anyways, we want to make this connection between these series, which are basically just infinitely long polynomials. I mean, we've dealt with things like the series of -1 to the n times maybe 1 all over 3 to the n, right? So we're going to replace the 1 over 3 with like a variable. So -1 to the n times x to the n. And this thing here will be kind of a polynomial. So if you start at n equals 0 and then go to infinity, I mean, what do you get? You get an infinitely long polynomial. The first term would be 1, and then minus x, and then plus x squared, and then minus on and on and on forever. But at heart, when you plug in 1/3, you're just getting a very simple series that we've been studying, the type we've been studying in sections 9.1 to 9.6, right? So anyways, again, we're making this connection now to these infinitely long polynomials, and those infinitely long polynomials will basically be ways of figuring out the value of sine of 1.5. Okay, so hopefully that gives you some sort of motivation for what we're doing. Anyways, let's take a look. So we'll be looking for polynomial approximations first, and then you'll basically take the polynomials to the infinite extent, like a series. And okay, so polynomial approximations first. We usually begin with something simple like e to the x, and yeah. So example 1, I think we're just going after a first degree approximation of e to the x. So example 1, approximate f of x equals e to the x with a first degree polynomial. And generally we want to begin with some center, so we're going to pick c to equal 0. Okay, so our first degree polynomial will write p sub 1, where the 1 stands for the first degree, of x equals a sub 0 plus a sub 1x. So it's just, your y equals mx plus b form. What we want is for the function and its derivatives to equal the polynomial. at the center. Okay, so the function is e to the x. Kind of butchered the e. So f of x equals e to the x. Its derivative is e to the x, and then evaluate these at the center. And we want those values to be the same as the polynomial and its derivative evaluated at the center. Okay, so anyways, the polynomial p1 of x, of course, is a sub 0 plus a sub 1x. Its derivative, p sub 1 prime of x, would just be a sub 1. Okay, evaluating them at c equals 0, the center, p1 of 0 is going to be a sub 0, and then p1 prime of 0 is going to be a sub 1. So all you're doing there is plugging 0 in for x into the polynomial and its derivative. Then, again, what we're saying is that we want the function and its polynomial to kind of be the same at the center. So first we want f of 0 to equal p1 of 0. So we wish f of 0 to equal p sub 1 of 0, and then we want also f prime of 0 to be the same as p prime of 0. So we want, just writing it in a consistent kind of way, f prime of 0 to equal p prime of 0. Okay? So we can figure out those the coefficients, basically a0 and a1, from these equations. So f of 0 is 1, p1 of 0 is a sub 0, so a sub 0 is 1. And then f prime of 0 is 1, p prime of 0 is a sub 1, so a sub 1 is equal to 1. So our polynomial, kind of just doing substitution then, is 1 plus 1 times x, in other words, 1 plus x. And you can see around the center, around c equaling 0, the line is really a pretty good approximation of the function. But as you get further away from 0, the function and the polynomial kind of start getting further and further apart. Right? So as long as you're really close, it's not a bad approximation. So in example 2, what they do is kind of take it up a notch. Right? They're going to, now let's look at the third degree polynomial. So let's look at example 2. Okay, so approximate f of x equals e to the x with a third degree polynomial. Okay, so again, we want the function and the polynomial to be the same at the center. We want the derivatives to be the same. So we'll set up some equations, right? So first, looking at f of x and its derivatives, we'll need to go up to the same degree, the same derivative as the degree. Okay, so we need to go up to the third derivative. And then evaluate all of these at the center. Of course, this example is pretty simple because everything is just equal to 1 here. You plug in 0 for x. E to the 0, of course, is just 1. Then we need to do the same thing for a third degree polynomial, and in this case, p sub 3 of x. You're going to go a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed. Okay, and then take its derivatives. So you would get a sub 1 plus 2 a sub 2x plus 3 a sub 3x squared. That should be the derivative. This is the second derivative now. So you get 2 a sub 2 plus 3 times 2. We're going to write that as 3 factorial because ultimately there's kind of a pattern that we'll use in order to figure out the approximating polynomials. Okay? So p3, the third derivative, is just going to be 3 factorial a sub 3. And then evaluate all these at 0. Okay, so the first guy is a sub 0, the second one a sub 1, the next guy 2a sub. So I'm just plugging in 0 wherever I see x in the polynomial. P sub 3, the third derivative will just be 3 factorial a sub 3. Okay. Then you're doing equations. You're equating the function and the polynomial at the center. So you get from the first f of 0 equaling p sub 3 of 0, you get 1 equals a sub 0. F prime of 0 equaling p3 prime of 0 is going to give you 1 equaling a sub 1. F double prime of 0 equaling p sub 3 double prime of 0 is going to give you 1 equaling 2a sub 2. In other words, in this case you have to solve for a sub 2. A sub 2 is 1/2. The third derivative equal to the third derivative of the polynomial, evaluated at 0. You're getting now 1 equals 3 factorial a sub 3. Okay, so in this case a sub 3 will be 1 all over 3 factorial. Okay, now we can back substitute into the polynomial. So p sub 3 of x is going to be 1 plus 1 times x plus 1/2 times x squared plus 1 over 3 factorial times x cubed. If we wanted to do this in general, so we're kind of trying to identify a formula that would give us a polynomial approximation for any function so long as it has derivatives and you can evaluate it, we would say in general, kind of just looking at this example, what do we have? P sub 3 of x is actually equal to, well, f of 0 would give you the a sub 1 plus f prime of 0 gives you, f of 0 gives you a sub 0, right? Then f prime of 0 would give you a sub 1, right? And then times x plus f double prime of 0 kind of gives you a sub 2. There was like some division involved, right? So it's really f double prime of 0 divided by what ends up being a 2. And the 2 just comes from the repetitive derivatives, okay? So you're always kind of coming up with the same numbers no matter what, because in your polynomial approximations to make these equations, you're always going to end up with 2a sub 2 as your first term and p sub 3 double prime, right? So you get f double prime of 0 divided by this 2 that comes from the exponent when you keep taking the derivatives, and then times x squared plus f triple prime of 0, but then we had to divide by a 3 factorial times x cubed, okay? So that's kind of the general formula for a third degree. If you just want an nth degree polynomial, in general we write that p sub n of x would be equal to f of 0 plus f prime of 0 times x plus f double prime of 0. Instead of writing 2, we'll write 2 factorial x squared plus f triple prime of 0 all over 3 factorial times x cubed plus dot 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 plus the nth derivative evaluated at 0 all over n factorial times x to the n. And this thing is called the nth degree Maclaurin approximation of a particular function f of x. Okay, so this thing is the nth degree polynomial or nth degree Maclaurin polynomial in particular. So let's maybe make that clear. Nth degree Maclaurin, M-A-C, yeah, Maclaurin polynomial for some function f of x centered at c equals 0. If c is not equal to 0, they call that the Taylor polynomial. So for c not equal to 0, we have an nth degree Taylor polynomial for f of x. Okay, so the formula for that thing is actually more general, I think. So p sub n of x would equal f evaluated at whatever the center is now. So if the center was 0, you just get the Maclaurin polynomial. Okay, and then f prime of c times, and then instead of writing x, you're going to write x minus c. Normally it would be x minus 0, right? And then plus f double prime of c over 2 factorial times x minus c squared, plus on, plus the nth derivative evaluated at c all over n factorial times x minus c to the n. Okay, so that guy right there is our Taylor polynomial for f of x. Okay, the approximations are better the closer you are to whatever the center is, and that's kind of what they're looking at in example 2 here with the chart. Note, as you get farther and farther away from 0, the approximation of e to the x with the polynomial is worse and worse. Okay. Also, I don't think they talk about it, but the higher the degree, the better the approximation. Okay, so the 4th degree is going to give you a better approximation, and the 5th degree better still, etc., etc. Okay. Next in the book, what they're doing is generating those formulas, the general formulas for the Maclaurin and the Taylor polynomials. And then they're kind of just doing things in general. So, for example, if they want the nth Maclaurin polynomial for e to the x, so find the nth Maclaurin polynomial for f of x equals e to the x. So automatically the Maclaurin means it's centered at 0. Rather than having to go through the business of taking the polynomial in general and taking off its derivatives, now all you need to do is basically this portion. Okay, and because of the way this is set up, you know what f of 0, f prime of 0, f double prime of 0, and all that jazz is. It's just 1. Okay, so your nth degree Taylor or Maclaurin polynomial approximation, in this case for that function, you're just filling in the blanks into this polynomial here, right here, that I just pointed at in red. Okay, so you're just going to get 1 plus x plus x squared all over 2 factorial plus x cubed all over 3 factorial plus x to the 4th all over 4 factorial plus dot 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 plus x to the n all over n factorial. Okay, and you look at that, that's really kind of like an nth partial sum, right? And then if we take the limit of that thing, we're hoping that that will actually equal e to the x, and we'll be coming to that conclusion in section 910. So we still got a little bit of work ahead of us, but eventually we'll get there. Let's do something other than e to the x, right? So e to the x is pretty simple because of its derivatives, but then you'll come across examples like number 4, finding the Taylor polynomials for f of x equals ln x, and this time it's Taylor. We want to center it at c equals 1. Okay. They want you to find p sub 0, 1, 2, 3, and 4. Let's just find p sub 4. Okay. All right, so first I'm going to have to go and get the derivatives all the way up to p sub 4, or all the way up to the 4th derivative, because it's a p sub 4, 4th degree polynomial. First derivative is 1 over x. Take the derivative, I'm going to rewrite it as x to the negative 1. Then I'm going to get negative x to the negative 2. And I get positive 2x to the negative 3. fourth derivative, -6, and rather than writing -6, I'm going to write -3 factorial, x to the -4. So factorials will pop up all over the place for us. Then all you have to do is evaluate these guys at the center. ln of 1 is 0. 1 to -1 is 1. -1 to the -2 is -1. This will be 2. This will be -3 factorial. Okay, so our Taylor polynomial P4 of x, and sometimes I like to kind of think of it as a fill in the blank. So it's, f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared all over 2 factorial plus blank. This will be x minus 1 cubed over 3 factorial. And then the last guy, whatever that is, times x minus 1 to the 4th all over 4 factorial. So kind of get it all set up, and then you're just copying and pasting those. So 0, 1, -1, 2, -3 factorial. And then kind of think about how the factorials will simplify. If you have n factorial all over an n plus 1 factorial, that'll just equal 1 over n plus 1, right? So what are we getting? X minus 1 minus x minus 1 squared over 2 plus 2 over 3 factorial is the same as 2 all over 3 times 2 times 1. So that's equal to 1 over 3. So you have x minus 1 cubed all over 3, and then minus 3 factorial over 4 factorial is promised. That's just 1 over 4, right? So it'll be x minus 1 to the 4th. Okay? And that gives us a 4th degree polynomial approximation for ln of x. Okay, this is important then because that's going to allow us to figure out what's the ln of 0.001. All you'd have to do is plug, so if you wanted to know something like ln of 0.001, you could basically just plug 0.001 into this polynomial. Okay, and then evaluate that, and you'd have some sort of answer. Okay, it may not be a great approximation, but it would be something. Okay, so they're kind of showing you what these compare and contrast. Clearly, you need to look at numbers around the center. I used a number around close to 0, so maybe it would be better if I used like 1.000 or 1.001 would be a better. I'm trying to get the right color here. There we go. Okay, so that would be better for doing approximation there. Figure 9.15 shows you the kind of sequence of polynomials. So approximating in the first picture with a first degree polynomial. The second picture shows you approximating with a second degree polynomial, which is a parabola. So you see the curviness kind of becomes closer to the curviness of f. So as you equate higher and higher derivatives, you're going to get more conformity, right? Because that first derivative will ensure the polynomial and the function are both increasing or decreasing. Then the second derivative will give you concavity, so the concavity will be the same shape around that number 1. And then the fourth derivative, I don't know what the heck that does, but it conforms it better and better to the actual function. Okay, it's kind of interesting to look at that as you get bigger and bigger polynomials. Okay, let's look at another example. So here, example 5. I want to find a Maclaurin approximation P sub 6. So find P sub 6 of x for f of x equals cosine x about c equals 0, right? Okay, so in other words, a Maclaurin. So it's the same, game. I need to start with cosine, and then it looks like I'm going to need to go up to the 6th derivative. and then evaluate them all at 0. And if you want to, instead of writing the Roman numerals, you could just put like 6 in parentheses. That's the same thing. And then I want p sub 6, a Maclaurin. So it's going to be blank plus blank x plus blank x squared over 2 plus blank x cubed over 3 factorial plus blank x to the 4th over 4 factorial plus blank x to the 5th over 5 factorial. I'm going to smush it in plus blank x to the 6 over 6 factorial. Okay, and then I could just fill all the material in. So we need negative cosine is 1 at 0, sine is 0. So you get that. And then copy and paste. And then make it look pretty. Oops, it's 0x. So interesting thing then about cosine, it's an even function, and the polynomial that you produce only has even powers, right? So the second term, negative 2, and then plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. It'll turn out sine has all odd terms, so if you kind of know cosine, you'll automatically kind of know sine, because p sub 6 for sine then for the sine function is just going to be x minus x cubed over 3 factorial, kind of the missing terms, right? And then plus x to the 5th over 5 factorial. The 6th term will be 0. Okay. And then they're showing you p sub 6 on top of cosine. So p sub 6 is a really good approximation in between almost negative pi and pi. So it's, you get a pretty good approximation. Example 6, they're looking for a Taylor polynomial for sine. Okay. And you see it's a bit nastier when you're evaluating the derivatives at pi over 6, right? Approximation using, okay, so example 7, now we're actually going to start doing some approximations of the functions. In particular, we want here to approximate the find an approximation for ln of 1.1. So what you want to produce then is some sort of nth degree polynomial centered at 1. Okay, so something close to 1.1. And here the book is telling you they want a 4th degree Maclaurin. Okay, so actually they're centering it at 0. And it even says in their solution you should consider a different Maclaurin. So to get around the issue that it's so far away from the center, what they do is use the function g of x equals ln of 1 plus x. Okay. Otherwise, this thing will be way off. Okay, so yeah, let's use that. They want a 4th degree Maclaurin. After we do some of these doing approximations, we need to kind of figure out how good is the approximation given like 4 terms or 5 terms. And then the reverse side of that coin is how many terms do we need in order to keep our error kind of bounded below some arbitrary value. Okay, so it's those 2 questions. We kind of saw those already with the alternating series estimation issue. But anyways, I'm going to have to go to the 4th derivative. Over here. Whoops. And then over here I have to evaluate them all. And then I'm going to go to my polynomial, just kind of set it up as a fill in the blank. I have to get all the busy stuff done first. Blank plus blank x plus blank x squared over 2 factorial, which you could just write as 2, plus blank x cubed over 3 factorial, plus blank x to the 4th over 4. Okay, we're ready. So the first derivative, 1 over 1 plus x, 1 over the guts times the derivative of the guts. That will just be 1 plus x to the negative 1. Then you do power rule, so negative 1 plus x to the negative 2. And then positive 2 times 1 plus x to the negative 3. And then negative 3 factorial times 1 plus x to the negative 4. Evaluating them all at 0, you get 1, negative 1, 2, and then negative 3 factorial. How did I get? Oh, so the first one, sorry, is 0. I was off by 1. G of 0, plug in 0 for x, ln of 1 plus 0 is ln of 1, ln of 1 is 0. Okay, and then we have it. So this will be 1, negative 1, 2, and 3 factorial. Negative 3 factorial. Okay, so splice those in. It's kind of very computationally dry at this point. And then make it look pretty. So x minus x squared over 2 plus x cubed over 3, because 2 over 3 factorial is 1 over 3, minus x to the 4th over 4. Okay. It's a nice thing to approximate it. Now you can actually plug in a piece of 4 of 1, because if you plug in 1, well, 0.1 rather. If you plug in 0.1, you're looking, it'll be approximately the ln of 1.1, right? So you're plugging in 0.1, so it'll be 0.1 minus 0.1 squared over 2 plus 0.1 cubed over 3 minus 0.1 to the 4th over 4. You can literally do this by hand. In other words, you can now figure out the ln of 1.1 by hand without a calculator, which is kind of a crazy thing. But we will use Wolfram to get that, whatever the heck that number is. 0.1 minus 0.1 squared over 2 plus 0.1 cubed over 6 minus 0.1 to the 4th over 4. Oh, whoops, over this. I was thinking that was a 3 factorial. It's just 3. Okay, so 0.0, it looked like 9 something. .0953. And then we can see what it actually is supposed to be. ln of 1.1, 0.0953. I mean, unbelievable. You know, it's kind of awesome, isn't it? So yeah, you can do that stuff now. All right. They did the approximation, and they're looking at different degrees, how good the approximation for different degrees, and then they get up to the 4th degree. And kind of compare and contrast that stuff. And again, you know, the farther you get away from the center, the worse the approximation, and the higher the degree of the polynomial, the better the approximation, right? Okay, so now we want to work with, all right, how good are these approximations? How many terms do we need in order to get some sort of approximations? And we have to work with this Taylor theorem. Okay, so section 2, I guess. Did I ever even introduce section 1? I guess polynomial price. Okay. So section 2, we're looking for remainders. This remainder theorem. Seems like I called it. Okay, whatever. Remainder of a Taylor polynomial. And it's kind of similar to the estimation theorem for alternating series. So if you recall, it's not that it's derived in the same way, it's just it's similar. So if you already know the estimation theorem, the what did we say, sorry for butchering my letters, s minus s sub n is kind of less than or equal to the next term in line in the series. Now it's kind of almost the same thing. Our formulas look a little different. So now we have some function f of x, and we're subtracting, we're seeing the difference between f of x and this p sub n formula. Okay, it'll turn out that we're going to call this thing some r sub n of x. It'll turn out that this thing is less than or equal to kind of the next term in the Taylor series, kind of. Okay, it's not exactly that easy, but it's very similar. So the next term in the Taylor series would have been the n plus first derivative evaluated at some number x divided by n plus 1 factorial times, and here's where it's going to get a little different, the absolute value of x minus c to the n plus first power. But if you think about it, that's exactly the next term in line in the Taylor polynomial. If you look back at the form of the Taylor polynomial, there it is. It's like the next term would be basically what we're using as the in the approximation, sort of. Okay, I'm lying a little. It's not exactly this, but it gives you some way of kind of remembering, okay, if you have nothing else. So sort of. Okay, so what exactly is this thing? Why did I leave the parentheses open there like that? Okay, so the actual error, which I just kind of hit on over here, is basically Taylor's theorem. It comes from Taylor's theorem. So you have this theorem 9.19, and if your function obeys some criteria, so the thing is differentiable up to the n plus first derivative, and in some interval around the center c, then for each x in that interval there exists some z in between x and c such that we can approximate, or actually find, this function r sub n, which is kind of your error function, or the difference between the function and the polynomial. Okay, so we could say that conclusively this thing, which we are saying is the difference between f of x and p sub n of x, this r sub n of x thing, the r sub n of x will equal the n plus first derivative evaluated at some value c in this interval between x and the center, okay, divided by n plus 1 factorial. Instead of using c, let's use z because we already have a c defined. Okay, z, and then times x minus c to the n plus first power. It seems to me this thing is derived somehow from a higher dimensional version of the mean value theorem. I saw it proved once, like in grad school, and I just said, okay, that's great, and kind of left it at that. Yeah, so they're pointing out to that. It's that theorem you've seen before, the mean, I think it was the mean value theorem. Yeah, it's the mean value theorem. This is kind of like, it becomes like a higher dimensional version of it, or somehow, or something like that. It's kind of foggy. It's been 20 years. So yeah. Okay, so theorem 9.19 says that the difference between the function and the polynomial, you can find it. You can figure out a function to represent that thing. But in working and sort of in practice, we won't work with finding that thing. In practice, what we'll do is just kind of bound the error. So in practice, we will find an upper bound, which will be on this absolute value of r sub n of x, and it will be the maximum of the n plus first derivative, the absolute value of the n plus first derivative on this interval from x to c or c to x, depending on whether your x is above or below c. So I'll just say on the interval from x to c. but it's more general than that, right? X could be bigger than C. Anyways, divided by n plus 1 factorial times the absolute value of x minus c to the n plus first power. Okay. Alrighty then. So let's take a look at example 8. And here we have a third degree polynomial already derived for us. So p sub 3 of x equals x minus x cubed all over 3 factorial. They're saying it's Maclaurin. In other words, the center is 0. They want to use Taylor's theorem to approximate sine of 0.1 by p sub 3, basically to determine the accuracy of that approximation. So, right. So let's take a look at that. So to work with this r sub n thing, there's a lot of variables floating about, right? There's n, there's x, there's the c, there's this max thing, and yeah, that's about it. So there's 4 things basically. So when I start these, I kind of try to identify all that information. So in particular, they want sine of 0.1, right? So the x is 0.1. The n is given as 3, third degree polynomial. Again, x is 0.1. The c value is 0. And then we still have to figure out this max of the absolute value of the first n plus first derivative on this interval. And the particular interval here is going to be 0 to 0.1. Okay, so the only thing I really don't know at this point then is that maximum. So somehow I got to figure that out so I can kind of flesh out this r sub n formula. Right now, r sub 3 of 0.1 is going to be less than or equal to this thingamajig that I don't know yet, the max of the n plus first derivative on that interval, and then divided by n plus 1 factorial. N we said was 3, so it would be 4 factorial times the absolute value of 0.1 minus 0, c is 0, to the n plus first power, which of course is 4. So I just have to figure out the blue thing. Okay, so we need to figure out what goes in the blue box. Okay, great. So what goes in there? Let's figure out what the heck the n plus first derivative is, right? So we can do that. Consider so what is the fourth derivative? Honestly, it's either going to be sine, cosine, negative sine, or negative cosine. And for all those functions, the maximum will be 1. So you could literally just put a 1 in that blue box and you'll probably be right. Okay. You could be a little more technical about it and say, okay, the fourth derivative, I mean, it's an absolute value, so it's either going to be cosine or sine, right? So, but anyways, f of x is sine. F prime of x is cosine. Double prime of x is negative sine. F triple prime of x is negative cosine. And then, of course, we're back. F4 of x is back to sine of x. So we're figuring out the maximum of that thing, the absolute value of that function. So, so we note the absolute value. So I need to maximize the absolute value of sine of x on this interval from 0 to 0.1. I could use sine of 0.1. I have a feeling that would be the maximum on that interval. But what I'm going to do instead is just use the idea that sine is always bounded above by 1. So we know, the general factoid that sine is in between negative 1 and bounded above by 1 everywhere. So therefore the max of the absolute value of sine on this interval should be less than or equal to 1. And so we'll use that in our blue box, okay, up there. I mean, you could get better, but then you would have to figure out what sine of 0.1 was, and we don't know what that is. Right? That was the whole point, is we're using a polynomial to figure that out. So anyways, putting 1 in that blue box, again, what are our special values? N is equal to 3, C was 0, X was 0.1, and now this max of the n plus the absolute value of this n plus first derivative, we're going to bound above by 1. So r sub 3 of 0.1 is less than or equal to 1 all over 4 factorial times 0.1 minus 0 is just 0.1 raised to the 4th power. And then, of course, you could figure out what the heck that thing is. So 1 all over, what the heck is 4? 4 times 3 is 12, times 2 is 24, times 0.1 raised to the 4th power. Of course, it's going to give me something I don't want. 0.1, 2, 3, 4, 5, 4, 1, 6 repeating. Is that right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and then into the 6. Okay, so you could see they have done the same thing as I did. So you're bounding above the sine of z thing, has to be less than 1, the max of sine on that interval. And then you could go and get a nice little approximation if you say that, okay, let's plug 0.1 into this polynomial above. So sine of 0.1 from the polynomial is approximately 0.1 minus 0.1 cubed all over 3 factorial, okay, whatever the heck that thing is. And of course we could go to Wolfram. Um, 599 over 6,000. So, again, the difference between the actual value and this approximation is going to be less than or equal to 0.02345, and then greater than or equal to negative 0.123454, and then you could solve for sine of 0.1 and you get this inequality. So whatever this thing is, this is so plus the 1 all over 4 factorial times 0.1 to the 4th. I think, let's make sure it's happy about this stuff. So on the top, we're thinking 0.099835, and then on the bottom, what are we doing? We're subtracting that, right? So it'd be minus. So on the bottom, I'm getting 0.099829 I guess. Okay, so let's see what the book says. 0. Yeah, mine's a little better than theirs, clearly. 0.0998. So their approximation was a little less than mine. That's why they got 0. It must have been they used they approximated the 0.00000416 repeating as 0.000004, whereas when I went in the Wolfram, used the literal value for that. Okay, so great stuff. Let's see what else kind of junk they have, and then they've actually figured out with the calculator, and they show it's pretty close. Okay, so now it's kind of the reverse side of the coin. Example 9. Let's go ahead and make this the video quiz for this section. So this will be the third video quiz in video quiz set number 7. So 9.7, it's example 9 from the book. Okay. So this time we're trying to approximate ln of 1.2 so that its error is less than 0.001. Okay. 0.001. We're going to use, we don't know the degree of the polynomial, but we want to center it around 1. Okay, so this time we can, instead of going ln of 1 plus x, which we probably should have done, we can instead consider our function f of x to be ln of x. Okay, and then we're going to be evaluating this thing at 1. Okay, so this time I don't know the degree of the polynomial. So what I'm going to do is kind of just iterate all the derivatives and find a pattern. So f prime is going to be 1 over x, which is x to the negative 1. F double prime, negative x to the negative 2. Triple prime is then 2x to the negative 3. Fourth derivative is going to be negative 3 factorial x to the negative 4. Fifth derivative is going to be 4 factorial x to the negative 5. So you can kind of see the pattern emerging, right? So the nth derivative is going to be n minus 1 factorial. So you see with the fifth derivative, you get 4 factorial. The fourth derivative, you get 3 factorial. The third derivative, you get 2 factorial. So we're going to have an n minus 1 factorial, and then x to the negative n, whatever the derivative is, you just get negative that derivative. And then there's a negative kind of oscillating, right? So we get negative 1, and when it's even, it's negative. So we want n plus 1. Okay. We're also going to need the n plus first derivative when we do our remainder theorem. So might as well get that out of the way. So we'll have negative 1 to the n plus 1. The thing you're taking the derivative of is x, right? It's with respect to x. So you'll have the n minus 1 factorial and the negative 1 to the n plus 1 are just constants in front. Then you do a power rule, so you bring down a negative n, and you get x to the negative n minus 1. And we could rewrite this a little bit. So we would have a negative from the negative n. That's going to give us negative 1 to the n plus 2, which is the same as negative 1 to the n, I believe. Then you're going to get n factorial, because n times n minus 1 factorial is just going to be n factorial. And then you get x to the negative n plus 1 if you factor out the negative. Let me make sure that's right. So, yeah, looks right. Okay. Likewise, then we get the function and the derivative at these places, and then look for the pattern. We don't actually have to do the approximation, though. We just have to figure out the number of terms we need for the approximation. So I think I'm just going to go up to this fifth derivative. Yeah, I don't even think I need to really do that, you know. Let's see if I can get away without actually having to figure those out, right? So Taylor's theorem then. And we get, you know, you have this r sub n of x. We need the kind of, what is n? Well, we don't know. What is x? Well, that's the 1.1, right? So we, 1.2. The c value, the center, we centered it at 1. And then we need to know the max of the n plus first derivative on this interval from the center to 1.2. So from 1 to 1.2. Okay, and it's the absolute value of that f to the n plus first derivative. Okay, so I could get everything except basically I need 3 of the unknowns, right? So I need to figure this guy out, and I can kind of figure that out from the n plus first derivative that I just found right here. Okay, right. So what I'm going to do first is get the absolute value of that. So the absolute value of the n plus first derivative is going to be the absolute value will get rid of the negative 1 to the n. So it's just leave you with n factorial times x to the negative n plus 1. Then you want to maximize this. Maximize, what does that mean? That means take the derivative. Okay, so let's call this thing, this new thing we just created, g of x. The derivative of that thing, so you need this to take the derivative, set it equal to 0, critical points, all that jazz. But it's a little different because we're on the interval. We want to maximize on the interval from 1 to 1.1. Okay, so it's a little bit different. Maximize on the interval from 1 to 1.1. Okay, so anyways, g prime of x is going to be negative n plus 1 times n factorial will be n plus 1 factorial times x to the negative n plus 1 in parentheses minus 1. So it's just going to end up being negative n minus 2. Okay. This thing on that interval is always negative, right? So on 1 to 1.1, if you plug any number in that interval into g prime of x will be less than 0. So what? Well, that means that the function is decreasing on that interval, and so its maximum will be at 1. So hence the max occurs at the left-hand endpoint at x equals 1. And so the maximum of the absolute value of the first derivative is just g of 1. And that equals n factorial times 1. 1 to any power is just 1. So g of 1 is n factorial. And so our max thingamajig here is going to be n factorial. Okay, so we can kind of flesh out our remainder theorems. So r sub n, I don't know n, of 1.2, the absolute value of that thing will be less than or equal to n factorial all over n plus 1 factorial, again I don't know n, times the absolute value of 1.2 x minus c raised to the n plus first power. So this thing equals n factorial over n plus 1 factorial is 1 over n plus 1. And then we have 0.2 to the n plus 1. And we need all of that to be less than the error that was given. We need it to be less than 0.001. Unfortunately, this time, unlike with the alternating series estimation theorem, you're not going to be able to kind of solve that inequality, right? So you're going to have to do trial and error. So, you start with a first degree, n equals 1, and you plug 1 into this formula here. So you'd have 1 all over 2 times 0.2 to the 2, and you want that to be less than 0.001, right? So you figure out what that value is. So what do we have? 1 over 2 times 0.02 to the second power, and that's 0.02 apparently. That's not good enough, right? That's not less than the 0.001. So I go to n equals 2. So I get 1 all over 3 times 0.2 to the third. That is 0.0026. Repeating, that's still not good enough. It seems like the next one will work, but you better make sure. So we have 1 all over 4 times 0.2 to the 5th, or rather to the 4th. Okay, so you get 1 all over 4 times 0.2 to the 4th, and that's going to work. So 0.0004 is definitely less than 0.001. So we need a third degree polynomial. We need p sub 3 of x. Okay, going back to the book and make sure we get the same answer. Yeah, p sub 3. Okay, all right. Is that it? Yeah, and then they go on the homework. Let's at least do one homework problem where we're doing this kind of game. Use Taylor's theorem to find an upper bound for the approximation of r sub 7. Okay, yeah, for e to the x, for the upper bound, I believe you just use 3. So for, what is this, number 9? So for the sine functions, sine and cosine, you're always going to, the max of the n plus first derivative will always be 1. Okay, but for something like e to the x, the max of the first derivative, you're going to suppose that is just 3. Okay, so note first off that e is less than, or well, it's definitely less than 3. Okay. Okay, so use Taylor's theorem to obtain an upper bound for the error of approximation, then calculate the value of the error. So we're dealing with e, and they've used what? They've gone up to, so e, if you think about the polynomial approximation, it'll be 1 plus x, and it's easy, x squared over 2 factorial plus x cubed over 3 factorial. And it looks like they've gone all the way up to, so e to the x is approximately equal to this polynomial, x to the 7th all over 7 factorial. This is p sub 7 of x. Okay, so that, it kind of looks like they use p sub 7 and a Maclaurin. So c is equal to 0. And then for this approximation, they're letting x equal 1. Okay, so in this case, x is 1. What else do we need? Center 0, x is 1. The n value apparently is 7. And, well, heck, I just said for the max of the absolute value of the n plus first derivative on this interval, and of course the interval in this case is going from 0 to 1, we're just going to say that's equal to 3. Okay, so the absolute value of r sub 7 of x, in this case 1, will be less than or equal to 3 all over 7 plus 1 factorial, so 8 factorial times 1 minus 0 raised to the 8th power, which is just 1. So you should just have r sub 7 is less than or equal to 3 over 8 factorial. They want a number, so whatever the heck 8 factorial is. 40320. 40320. 320. Okay, and then they actually want that approximation, so then you're going in plus 1 over 2 plus 1 over 6 plus 1 over 24 plus 1 all over, that was 4 factorial, so 5 factorial, which is like 120, plus 1 all over 6 factorial plus 1 all over 7 factorial. Okay, so r sub 7 of 1 should equal 685 over 252. About 2.71, which is e is about 2.71. Okay, so let's put that in. 685 all over 252. Let's see if that works. Oh no! 685 over 252. What the heck did I do wrong, man? Do they want an approximation? Oh, round the 5 decimals. You guys. Well, my answer's better. 2.71128225. 1, 2, 3, or 5. Still not happy. 2.718225. 2.71825. That's 1, 2, 3. What the heck did I do? Did I put it in wrong? 1 all over 4 factorial. All I can imagine is I screwed 3 factorial. 685, 250. I mean, the first number was right. 252. Push enter again. R sub 7. Oh, what is R sub 7 actually equals? No, I mean, oh, the remainder. So you got to take the difference. I apologize. So that basically minus, or rather, e to the 7 minus that, right? Or e to the first power. E to the first power minus this thing. Okay, so, geez, sorry. So this is 0.123455. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They want 5 decimals. Rounded 5 decimals. All right, let me pause the video and figure out what the heck I did wrong. No, I accidentally put another 0 in there. There's only 4 zeros. Boop. So my eyes aren't what they used to be. I apologize, computer. All right, so there's that. Okay, so I think it can handle everything else. We'll leave it at that, and then next time we're going to start trying to make the connection between these finite polynomials and the infinitely long polynomials, which are basically series, right? So trying now to make, in the next section, we'll try to make the connection between the series -1 to the n times x to the n from n equals 0 to some m. You know, this would be like a piece of m of x. And then we want to connect this to the infinite series n equals 0 to infinity of -1 to the times x to the n. It turns out that this, in special cases, will actually equal the function, and that's what we need to look at. And then we need to figure out for which values of x, you know, if it doesn't always equal the function, for which values of x will it work? You know, so you'll get what's called an interval of convergence, and that will kind of do it for us for chapter 9. But yeah, there's still a little bit long ways to go. We'll have to backdoor kind of the beginnings of this idea. We still need to work with intervals of convergence, so we'll start, you know, working with this thing and seeing where it does converge. And these guys are we'll look at these things, a sub n, x to the n, and they're called power series from n equals like 0 to infinity, and figure out which values of x it'll converge for. Then we'll kind of again make the connection, backdoor the connection, and ultimately end up with these infinitely long polynomials. Okay, so we still got a little bit ways to go. Anyways, I gave you the video quiz. Yes. Thank you for watching as usual, and I'll see you next time.